physics enthusiasts. You've probably seen such videos where metal is heated to red hot in a second, or blob of molten metal is levitated. But how does it exactly work? In this video, we'll start with a small piece of wire and build up our knowledge to complex inductors and understand the magnetic fields around them. The basic equation that we're going to need to use here is Biot-Savart law. We're going to use it extensively, so we have to understand it thoroughly before we move on. For those of you who aren't interested in equations, you can skip 2 minutes ahead. For those who are, let's do it. Expression number 1 is the Biot-Savart law. It states that a current carrying element dl with current I creates a magnetic field dB in distance of r. Note that dB is a vector, and vectors have direction, and this direction is defined by a cross product of dl and r. Note that r here is a full displacement vector. In other cases, in other sources, you're going to see it might be displayed in a different form. So the first expression is given from an infinitely small wire carrying current I. To calculate the magnetic field of the whole wire, we have to sum together pieces. And we do that by integrating across whole length L. Nu divided by 4 pi is a coefficient. So to simplify expression, we can take it out from the integral sign. Nevertheless, we are left with a pretty complicated expression for 2 reasons. First, it holds a line integral, and secondly, it has a cross product. One simplification of this formula that's often used is shown in expression number 3. There, instead of a complicated cross product of dl and r, we have a simpler term. It's dl times r times sinus theta. Here we have to know the angle between vectors, which is defined as theta. If we do, we get a lot simpler expression, since it gives us a scalar value. Note that then we have to know the direction where the vector will be pointing so we can use this correctly. So we have obtained some kind of relation how current causes magnetic field. And now let's apply it to a specific geometry. And the simplest case that's always examined is an infinitely long wire. And the magnetic field of infinitely long wire is shown in the sketch. And the lines you see are field lines. By their definition, they are lines with the same magnitude of magnetic field. To calculate the magnitude of magnetic field, we use expression number 4. In a not so simple steps, we can integrate it and derive expression 11. For those who are interested, you can pause the video and see how it's obtained. But here we are more interested in the result analysis. So the expression 11 states that magnetic field of an infinitely long wire is proportional to the applied current and inversely proportional to the distance r. And we can also see that there's only a radial component. To reiterate, if the current line is infinitely long, then there's no z component of magnetic field. In a graph, you can see the magnetic field of a wire which is carrying 10 amperes. It produces magnetic field with a magnitude of 0.01 millitesla. It's not that much if we compare it to, let's say, Earth's magnetic field, which is 0.05 milliteslas. If we increase the current, the magnetic field increases proportionally. So, if we apply 30 amperes, the resulting magnetic field is 0.03 milliteslas, which is still less than an example we chose, Earth's magnetic field. To increase the measurable magnetic field we obtain with infinitely long wire, we have to change the geometry. We want to maximize magnetic field. And one way of doing that is to change the geometry to axisymmetrical current loop, or simply called a ring. Magnetic field of it, it's is expressed in expression number 12. Here we can see that the magnetic field is a function of capital R, and capital R here is the radius of the ring. Furthermore, we can see that the magnetic field is proportional to a constant and applied current, but inversely proportional to the distance to the center. In a graph, we can see the characteristic values of magnetic field, which is produced by current ring. Here, the current is again 10 amperes, and the resulting magnetic field now is 0.06 millipascals, meaning that we have surpassed the Earth's magnetic field finally. Similarly, as in case before, when we increase the applied current, the magnetic field increases linearly. Quite often we are interested with magnetic field values along the symmetry axis. To calculate them here, we use expression 13. There, the small letter r is the distance to the point of calculation. However, we are interested in a projection to z-axis. In this case, it's just a z coordinate. And we need this projection to make our integration easier. We do substitutions in expression 14, where we express the magnetic field in terms of capital R and Z. And that's how we get expression 15, which is a lot simpler to integrate. Each current element causes magnetic field dB. This vector dB can be split in two parts. One part is dBz and another part is dBy. And when we integrate, each element causes the same dBz, so we can add them together. But dBy of each element is in a different direction, and when integrated, they cancel each other out. Mathematically, we use expression 16 to obtain dBz. There, we get it by multiplying cosinus theta to dB. Then we do the line integration in expression 17, and in the result, we obtain Bz in expression 19. Now, let's analyze this expression and plot the Bz as a function of distance z with a coil of 25 centimeter radius. Here in the results, the first thing we can see that the maximum value is observed in the center, and then it drops off symmetrically and quite quickly. In example, if we take 30 amperes, the resulting magnetic field is around 0.07 millipascals, which is again better than Earth's magnetic field. However, the magnetic field is not homogeneous. So, to get a homogeneous magnetic field, we have to devise something better than this setup. And here comes the next setup, which is excellent for field homogeneity. It's called the Helmholtz coil. And that basically means that there are two loops of wire which carry current in the same direction. To calculate magnetic field in between them, we can use the superposition principle, which means just to sum together each coil and the magnetic field which results from it. It's done in expression 20, and now let's graph it and see how it looks. There are two maximums in this graph which correspond to the position of the coil. Note that we've chosen the z-axis and 0 point arbitrarily. We could move wherever we want. That doesn't change the calculations. So, if we change the separation distance, which is done in the beautiful animation, you can see that at a certain range, we can achieve a homogeneous magnetic field. And in this case, it's around 30 centimeter separation distance. And this is really valuable for scientific experiments. Now let's move back from homogeneity to maximizing magnetic field. Previously, we have shown that the circular coil is better than equal to long wire in creating stronger magnetic field. Now let's try to capitalize on that and optimize the geometry even more. And one way to do that is add more coils with the same center with different radiuses. By doing that, we get what's called a planar coil. And magnetic field of planar coil can be calculated using expression 21, where, using again the superposition principle, we sum together magnetic field of each coil created. In the graph, you can see the magnetic field of each coil and how it falls off in the distance. But the most interesting curve is the total magnetic field. Since it proves by just having 4 coils, it tremendously increases magnetic field in the center. And for example, in case with 10 amperes, we can already get 0.16 millitekes, which is 3 times the Earth's magnetic field. Such setup is often used in cases where you have to have a strong magnetic field near a flat surface. Practical examples are induction stoves or wireless charging setups in cell phones, because there you have to have a really good magnetic coupling in a short distance. Finally, we have reached the most popular configuration, which is a multi-turn coil, or simply called solenoid. This is very important in the context of induction heating, since this maximizes the field inside of the coil, where the workpiece usually is. Mathematically, we can describe it as a collection of individual turns with the same radius but a different location. So the expression for calculation is number 22, where we sum together magnetic field of each coil created. But in this case, we've chosen the point of center point Z0 in the center of the coil. That's why we use expression number 23 for this specific calculation. In this graph, the distance between each turn is fixed, but amount of turns is changed. By doing that, we can see multiple things. First one, the magnetic field inside the coil increases. The difference is not huge, but it's there. And the second and more important thing is that the volume of a strong and homogeneous magnetic field increases. Also, with this exact separation distance, we can see a local maximums where each turn is, and that results in a pretty funky graphs. In the following animation, the distance between turns is changed. It shows that if the turns are closer, the magnetic field inside is more concentrated. And also that there is a certain threshold above which the turns are no longer visible as local maximums. With these visualizations, I wanted to show you, if the turns are plentiful and a distance is small between them, that the magnetic field inside of the coil is pretty homogeneous within a reasonable tolerance. And in such cases, a simplified formula in expression 24 can be used. With this, it's a lot easier to calculate magnetic field, and it's accurate if the conditions are met. Unfortunately, the calculations we made previously assume infinitely thin wires, no current terminals, and overall an axisymmetrical case. And even with all these simplifications, we can only calculate the values on axis with a moderate ease. If we want to do more advanced geometries, take account imperfections, and know the magnetic field everywhere around the coil, we have to use numerical methods. And in this video, I show you an example with a multi-turn coil where the magnetic field is calculated with a numerical software, COMSOL, multiphysics. Here we input the geometry of the problem, software reduces it to finite elements, and the computer calculates the sophisticated equations of electromagnetics. I'll use this extensively in my next video, since besides electromagnetics problems, as a bonus it allows me to calculate heat transfer, which is important in induction heating. Moreover, the software allows me to visualize things that otherwise could not. As an example, take this cross-section of solenoid, where the magnetic field intensity is indicated with a color. This perfectly illustrates how magnetic field intensity depends on the location. with the blue zones having the lowest values and the red zones having the highest values of the magnetic field. In the next video, I'll talk about induction heating, as why things heat up in alternating magnetic field. Skin effect, as what happens to magnetic field when it's in conductive media, and levitation melting. There, the focus will be less on equations and more on results of numerical models, and also on actual experiments with induction heating. All of the references I made in this video can be found in the description. And also, I will publish the Mathematica code I used to make all of these beautiful graphs and animations. If you like this video, you can subscribe, and maybe YouTube will notify when the next video is up. See you then!